Remember last week we learned about insolation, very important concept. The angle that the sunlight strikes our planet plays a huge role in biomes and climate. Energy can move in different ways, but the only one that works in space is the first one, radiation. And that's because radiation or electromagnetic waves do not need a medium to travel through, a medium being other atoms. But the other two forms, conduction and convection, those require atoms that touch each other or atoms that heat up and move. There are no atoms in space. But there are plenty of atoms, and they are relatively dense in our troposphere. Oh, we learned about that. That's the bottom layer where we live. Okay, so our troposphere definitely experiences conduction and convection. That's ways that energy can move in our system. The sun is our star, and it's the main source of energy. But when we think of the sun, the first thing that comes to mind for me is not its heat, but instead how bright it is. Right? Everybody knows you can't go out and just stare at the sun. And when we talk about electromagnetic waves, they belong to what we call a spectrum. And the spectrum includes visible light. But it's only a small amount. It's that tiny little sliver that you see about 2/3 of the way down. The sun is giving off all these other types of energies. It's giving off radio waves, microwaves, infrared, that's the heat. So when we do feel the heat of the sun, we're getting invisible waves of infrared. Ultraviolet, we don't feel the heat from ultraviolet, but it gives us sunburn. And then at the bottom, the highest frequencies and shortest wavelengths, those are X-rays and gamma rays. And those are nuclear. Basically, it's the nuclear products of the sun. And thank goodness our magnetic field blocks those. So UVA and UVB are kind of the worst that we get. The stuff at the far end does not enter our planet in large amounts. So thank goodness for the iron core and the electromagnetic field. We can actually view the sun in these different frequencies if we tune in with a computer, because they are invisible, but we can detect the waves and then decode them and create an image. You can see the sun is very beautiful in some of its other wavelengths, ultraviolet. Now, that's what we call a false color image. And that means that we had to assign a color to it because it's not visible. It doesn't have a color. But you can see the energy coming out at those high wavelengths. It's really dramatic. The sun itself is actually super boring. If you were to look at the sun through a normal visible telescope, don't do that. You need a special kind of telescope. If you did that, it would just be a round ball. Pretty boring, actually. If it has sunspots, it's a little more interesting. Currently, we're in something called a solar minimum. There aren't very many sunspots. We've got all these wavelengths, and look at this. The sun gives off wavelengths at all these different frequencies. The Earth also gives off energy. We know this, right? At nighttime, we leak heat into space. But do you notice the key word I said? I said heat. Heat is one tiny form of wavelength, and it's the infrared spectrum. That's how night vision goggles work. They sense the infrared. But yeah, the sun gives off way more energy and way more different wavelengths. The Earth, if it only took in all that energy from the sun and it only gave off a little bit at night, wouldn't we overheat? And the answer is, well, we don't, because of what's called the heat budget. And astronomers talk about the Goldilocks hypothesis. We are not too hot and not too cold. We are just right, like the Goldilocks story. And it's the idea that Venus is way too hot. It's closer to the sun. Mars is way too cold. It's farther from the sun. But we're right in the middle, and it's just perfect. It turns out that our atmosphere and our surface, being mostly water, is able to spread that energy out enough that we don't cook in space. Here's what you actually need to know, Okay, here's a simplified version, right? On the technical one, you can see some of it goes into the clouds, some goes into the atmosphere, some goes into the ground, some of it bounces back and forth, the greenhouse effect. Here's a simpler one. If we have 100 units coming in from the sun, about 70 of them get all the way down to our surface, about 70%. And what happens to the other 30? They just bounce back out into space. They go somewhere else. That's the magic number I want you to learn. About 30% bounces off the planet. Now, here's the amazing thing that our Earth does for us. If we take in 70 units a day, guess about how much we lose each night. It turns out it's the balance, 70% or 70 units. So the Earth does a tremendous job of keeping us stable, not getting too hot or too cold. Now, there are local variations to that. We have deserts. That's where we're heading. It's like, why do we have biomes when the Earth does a good job of trying to balance? Here's that magic number again, and the concept called albedo. And I think I introduced this last week. Albedo is how much reflectivity occurs, how much is reflected or bounced off. And as we just said, it's 30%. But that number can change based on a lot of factors. One of them being urbanization. One of them being melting ice caps. And all the things that are leading to climate change are actually tied into this concept of reflecting insulation. You have a basic understanding of this already. Lighter colors reflect, right? So ice caps do a good job of reflecting energy. If they melt, the land is going to absorb that energy instead and heat up the troposphere. Smooth surfaces reflect better than rough. So smooth, clear lakes, they absorb some of the energy because they're transparent, and they also reflect some because they're shiny and flat. Now, where humans play a role is architecture and land use. Think about urbanization. We pave roads. They're usually black or dark colored. They get very hot. Humans have drastically impacted how energy is absorbed, especially in cities. I thought I'd tie in a current event. This is Peter Gleck. He's a climatologist out in California. His specialty is water. He's usually talking about water. I do recommend you follow him if you're into environmental science. He speaks down at our level, and he is passionate. He is also very liberal. So if you're more middle of the road or conservative, you may not like him. But he's mostly spitting facts. So in California, they're experiencing the wildfires. And he's obviously a big proponent of solar energy. And he has his own solar panels at his house. And you can monitor how much energy they're producing at any given time. So obviously on a cloudy day, you're producing less. Here he has September 10th or 9th, from September 10th from last year. And that's the peak of how much energy was produced that day. And because of the wildfires, their atmosphere is thick with smoke. And because of all the smoke in the sky, the solar panels are not able to produce anywhere close to the amount of energy that they normally do. That is a huge difference, and a side effect we don't think of right away with the fires. Of course, the air quality is bad. People are losing their homes, right? We're losing carbon sinks of the forest, but also we're not producing as much renewable energy. So huge trickle-down effects of the forest fires happening right now. There's another factor that goes into our albedo, and it is the water that makes up this planet. In fact, it's disproportionate. There's an uneven distribution of land and water on our planet, and College Board wants you to know that. What we mean is that there's way more land in the northern hemisphere than there is in the southern. And because you have much more water in the south, it does a better job of balancing temperatures. Things are much more steady or constant in the south. Think of this, you go to the beach in Florida. It's 100 degrees out. The sand burns your feet, but the water's cold. Why? Well, because it reflects, and because it's transparent, it absorbs and spreads it out over a much larger area. called differential heating. The water doesn't get warm. It stays cool all year. It heats up a little. But the sand, you're only heating up that top layer. And that's why it burns your feet. Okay? So where you have more water in the south, it spreads that energy out in much greater capacity. In urban areas, we tend to be warmer on average because of all of our construction, because of the surfaces that do not absorb and reflect and store carbon. So anywhere that we have a city is called a urban heat island. So we'll see you tomorrow, and we have a very important lesson about global climate patterns.